So hi everyone to the week 6 of this Sobolev space and partial differential equations course, and we are having our TA session today. So my name is Shami and I'm a research scholar at IIT Delhi, and I'm currently working in the field of partial differential equations. So in this week, in the video lectures, you have studied about the more about the embedding theorems of the Sobolev spaces. That these Sobolev spaces are actually embedded in some of the LP spaces, and we have a classification. Like we have three type of embedding theorems, depending upon whether the value of p is less than the dimension, greater than or equal to the dimension, or equal to the dimension. So depending upon that, we are defining the embeddings. So we saw that embeddings, and ultimately the goal was the embeddings are coming at the end was coming from the inequalities. Sobolev, basically a Sobolev inequality, and then we have this Moore inequality, and then we have another inequality. And once we have those inequalities, we use these inequalities to reduce. We have a continuous embeddings into these embeddings of Sobolev space into the LP spaces. So in today problem session, we will derive some likewise inequalities, and that will help us in like changing the norm or like having an equivalent norm on the spaces. So they are quite useful in that because sometimes we want to deal with some particular portion of the norm and like some particular part of the norm, and we want to show that particular part to be norm as well. So in that spirit, let's start our problem session. So the first problem is integrate by parts to prove the interpolation inequality. And what is that interpolation inequality? That is norm of tu L2 is less than equal to c times norm of u. Del 2 of u is for half, and then we have norm of d to u. L2 is for half. For all u in is infinity of u. Next, assume this neighborhood u is bounded. Del u is smooth, and prove this inequality then. If u belongs to h2u intersection h0 1u. So where actually let me also denote what do I mean by du and other stuff. Du is del u by del x1, del u by del x2, del u by del x1. So this is nothing but a gradient of u. That's the notation. And d square u is actually the matrix del square u del xi del xj ij, and they are going from 1 to n. So this is the matrix notation. So del d2u is just a matrix only. So the matrix of all the second order partial derivatives for u. We need to prove this inequality. So to prove this, we start with the du L2 square. So let's see what this thing is. So it's u du dot du. So actually this is just mod du square, but this is nothing but the norm u du dot du. And this is actually if we apply the integration by parts, this is nothing minus of u times. So it's a d with du. So it's like d dot du. And when we see this at d dot du, this actually turns out to be a Laplacian of u plus the boundary term at u du, and then we have this dot product with the normal unit vector. But this is zero because this is by integration by parts. So this is nothing but minus u times Laplacian of u, and the boundary term vanishes because my u is zero in the boundary. Now I can use the Cauchy's inequality to eventually land up with that the du of L2 of square is less than equal to u of mod u square. This is Cauchy's cos. So next, when I've applied the Cauchy's cos, or basically held there at p equal to 2. So now this is nothing but the L2 norm of u, and next we have this thing to be actually Laplacian and trains the only the diagonal terms of this d to u. So this is definitely less than equal to d to u L2 norm. Ultimately, this implies that this d to u L2 is less than some constant time u L2 half, and then d to u L2 half for all u in Cc infinity of u. So we have this relation holds that's what we want. So ultimately we have, sorry, this is just du only. So we have the relation for the we have the inequality for the case whenever my u is from a compactly supported C infinity function. Next, we want to prove this inequality for u in h naught 1 u intersection h 2 u, provided u has the property that it is bounded and moreover that del u is smooth, so boundary is smooth. So the main idea here is that since del u is smooth, we can extend the our function, Sobolev function, without any hurdle. So since del u is smooth, so u is smooth, so and extension operator exists. So once this exists, I have this u to be extended to the whole of the Rn, and once that's we have this density theorem which we did that finally the what this implies we have then they exist a sequence sequence in then there exists a sequence wk k from 1 to infinity in c infinity u bar such that the wk converges to u in h2 of u. So we have one sequence in h2u because by using the density of our this basically CZ infinity functions of Rn in the extended operator H2 of Rn, but since you have the extension operator to exist, so ultimately we can restrict this WK to the U bar and ultimately we have this convergence. Moreover, as U belongs to H0 menu, so now using the definition of this H0 menu, we have this, then there exists another sequence Vk, k from 1 to infinity, such that Vk converges to U in the H0 one now. So we have two sequences, this, and somehow we have to use the inequality which we have derived from CC infinity functions. So one thing we can observe for this, the crucial thing which we have to observe to prove the inequality for the H0 one intersection H2 functions is that when we prove the inequality for the CC infinity functions, we see that the one thing that the support actually vanishes here. So this thing vanishes only if u is zero. That is, if u is zero, that is enough for us. So we don't need any restriction, need any condition that we also has to be that again we the another function. So if we instead of considering du by du, I can consider du or du times dv, and that doesn't require another function to have zero on the boundary. So using this crucial fact, we have one this relation that if I start with u, so I'll start with let's say u du. So let's start with dwk dot dvk. So since I know that vk vanishes on the boundary, that much I have to already require. So I can write this as a whole u and d of so d dot of dwk whole of pk. This is my by indication my path and plus again the boundary of u of dwk times the unit vector times vk. But as again we have vk to be in cc infinity. So that's why I forgot to write that vk is in cc infinity u such that this thing holds. So then we have the complex suppose so this integral is actually vanishes. So this thing is actually nothing but the minus u Laplacian of wk times vk And then here again we can use the triangle inequality, Cauchy's quasi inequality or Heldon inequality to achieve that. This the integration of u dwk dot dvk. This is actually less than equal to the L2 norm of vk, and again the L2 norm of Laplacian of wk. But again that is less than d2u, so we can again replace this thing by this thing u vk square half u, and then we have d2 wk square whole is power of half. Now what do we know? That this vk converges to u in h01, so it converges in the h01 norm. So that means consider in the right hand side. So let it this to be star. So RHS of star as vk converges to u in h01 norm, then u vk square whole is power of half. This thing converges to, so this converges to u square whole is power of half, because again h01 implies by the point inquiry we have this convergence as k tends to infinity. Also, we have this u d2 wk square whole is power of half is also goes to integration of u d2u square whole is power of half as k tends to infinity. And this again comes from the fact that in wk converges to u in h2 norm. So h2 norm actually have this d2u factor. So because of that, we have again the convergence. So the right hand side is actually converging to the what we want in the inequality. All we have to take care is the left hand side. So let us consider the LHS of star. So LHS of star is integration of u dwk dot dvk. So we have to consider the convergence when we have this thing. So can how to write this? How to evaluate this? We can do one thing that I can write this as dwk minus du dot dvk plus u of du into dvk. And again, this can again further written as u dwk minus du dvk plus u of du times dvk minus dv, and finally we have this for dvk minus du times du. So we consider the difference of this thing dwk dot dvk minus integration of u of du dot du. This thing is less than equal to the modulus of individual of these things. So this is mod u minus dwk minus du dot dvk plus integration of u of du dot dvk minus du. So now we can employ the Cauchy's path inequality. So we have this integration of u of t wk minus du square whole is power of half, and then integration of u times tvk square whole is power of half, u of du square whole is power of half, and finally we have u of dvk minus du square whole is power of half. But again, we know that since vk converges to dvk converges to u in h0 norm, so we have the gradients to be converging in the L2 norm. So this side inside goes to 0. This is bounded. This thing goes to 0. This again goes to 0 as W converges to U in H2, as VK converges to U in H01. And finally, this thing actually is bounded. And why this is bounded? Because we have this is a VK is a convergent sequence in H01. So it's a convergent implies boundedness. So this is bounded. So this implies as k tends to infinity, integration of u d wk d dot vk goes to integration of omega u of du dot du. Thus, we have what? Thus, we have finally our required inequality, which is the integration of u of mod du dot du mod is less than equal to the right hand side, and right hand side is this thing. Then the integration of u of mod u square whole is power of half, and then we have mod u integration over u of mod of t to u square whole is power of half, and this holds for all u in h01 u intersection h2 u. So this completes the proof, and the only crucial point which we have to observe is that we can have this integration by parts to be evaluated with different functions u and v. So that was the main crucial idea, so that we can use different sequences. So this actually interpolates the inequality that we can actually remove this du factor. In the when we consider the norm, we don't need to really consider the inner basically the what would say the middle derivatives. So in this case, since we are considering up to the second order derivative, so we don't really have to consider the first order derivative when we are basically considering the norm. So only the first function itself and the highest order derivative. In fact, the more general thing is also true. You have something like that thing. So we ultimately not really need to consider the middle order derivatives. So yeah, that's something which we can infer here. So in this H2U intersection H01U, we can have this norm to be of this form. So this what we have done is for the H0 or the Hilbert space. We can have one more type of inequality for the general Sobolev space when my exponent is in general P. So based on that, we have another question. So Question number 2 is part 1 is integration by parts to prove du and LP less than equal to constants time u LP half d2u LP whole is power half. So the sort of same inequality, but now we have instead of L2, I can have the same sort of inequality for the LP space, but that holds for all P which are greater than or equal to 2 and all U in PC infinity U. So let's try to prove this inequality. Mm, Solution. So since we have a CC infinity function, we don't really have to bother about this derivative. Like we can have the classical derivative. So we can actually directly do the integration by parts. So let us start with again. Consider du LP whole square of t. So this is nothing but integration over u of mod du whole square of t. This again can be written as integration of u mod du whole square of p minus 2 du dot du. So I can write this because mod du dot du is nothing but mod du whole square. And again p is greater than 2, greater than or equal to 2. So this one can write. So next I can use the integrate by parts. What do we have? We have this minus u. So d of mod du p minus 2 du, then just a u only. So just a product multiplication by u only. And then we have this boundary term of mod du p minus 2 u and du dot with the unit normal. So it's the unit normal. So this will be different for each x, but I am not writing it, but that one can assume that it is actually changing with respect to the point which I'm considering on the boundary. But since u is 0 on the boundary, so the boundary term vanishes, and ultimately we have this thing that this is minus u. So when we do this d of this thing, this will be nothing but p minus 2 mod du p minus 4 du dot du, and then there's a Laplacian of u, and plus we have mod du p minus 2 into Laplacian of u only, and whole multiplied by u only. So if we see, basically this is nothing but something less than equal to some constant times integration of u of mod u or du whole is for p minus 2 and mod of Laplacian of u. Now, to deal with this, we will apply Hölder inequality. So we first go with this module. So here we just apply with the Laplacian u is for p 1 by p. So the exponent, the conjugate exponent is nothing but p upon p minus 1. P upon p minus 1 whole is power of p minus 1 whole divided by p. This is something constant, and this is again less than equal to the d2u of p times 1 by p. So this is something which we have wanted on the right hand side. And again, this is nothing but the integration of u over mod du is power of p minus 2 p whole divided by p minus 1 and mod u whole is power of p upon p minus 1. So this is comes from Hölder inequality. Is further less than equal to c times some u d2u whole is power of p whole is power 1 by p. Again, we again apply Hölder inequality with the exponent p minus 1. So p minus 1 is actually greater than equal to 1. So p minus 1 is greater than 1 is equivalent to p, saying that p is greater than equal to 2. So we can again apply Hölder inequality. This is integration of u mod u power p minus 1 divided by p and whole power. This will be p minus 1 upon p minus 1, and we have mod du p minus 2 whole divided by p minus 1. So we have this, and the exponent will of p minus 1 is p minus 1 whole divided by p minus 1 minus 1, and this is p minus 1 whole time divided by p, and we have to divide by 1 by the conjugate exponent of p minus 1, which is p minus 2 divided by p minus 1. Again, this is by Hölder inequality. This is less than equal to c times and this is again the mod u p whole is power of 1 by p, and this is u mod du whole is power of p only, but this is nothing but p minus 2 whole divided by p. So eventually this implies so we started with du lp whole is power of p. This is du whole lp whole is power of p, and we have to minus this thing, which is nothing but p minus 2 The whole square of p is nothing but d. So this is actually, let me write in this form. Integration of u mod du whole square of p 1 minus p minus 2 by p is less than equal to c times u d2u p 1 by p integration of u mod u whole square of p whole square 1 by p. So this is actually nothing but the du LP norm of du square. So this is p minus p plus 2, the 2 by p, and that is the square some constant time the d2u LP norm and the LP norm of u. Eventually, this implies du LP has to be less than equal to some constant time d2u LP half and u LP half, and this holds for all u in Cc infinity of u. So finally, this is the required inequality which we want. So we have our required inequality. So next we have a part B. So again, we have sort of the same interpolation equality. When I change my function, if I have changed my exponent from 2 equal to any general p which is greater than equal to 2. So we have again the same sort of interpolation equality. But again it actually it removes the case when it happens between p between 1 and 2. So there's another sort of interpolation inequality for the range 1 to 2. In fact, that is in general true for any p greater than equal to 1. So that's the part B, which is the second interpolation inequality. So prove that du L2p is less than equal to some constant time u of L infinity of half and d2u of LP raised power of half for 1 less than equal to p less than infinity and all u in Cc infinity u. The solution. So to prove this again, it's like starting with the left hand side, and we will see that what we do. We will try to use again Helder and integration of bytes. So eventually arrive with this inequality. So consider u in Cc infinity u, then the norm of tu L2p or s power of 2p is nothing but the integration of u mod du whole s power of 2p. So this again can be written as integration of u of mod du 2p minus 2. So again, p is greater than equal to 1. So this thing is valid. Du dot product d with du. And then you use the integrate by part minus u du of mod du 2p minus 2 du times u plus the boundary term plus the boundary term. So the boundary term The boundary term can be the boundary term is actually again vanishes. Mod du 2p minus 2 uh, du times u, and actually in fact we have this u times du dot the unit vector. So this everything can be written as this thing again vanishes because u is 0 on the boundary. And here we have actually all this thing coming from the integration by parts minus u is 2p minus 2 mod du 2p minus 4 du dot du plus mod du whole square of 2p minus 2. Then it will be uh, du dot du is actually a Laplacian of u, and also we have Laplacian here as well, whole into u. So this is nothing but eventually less than equal to the integration of u with some constant mod du whole square of 2p minus 2 mod of Laplacian u into mod of u, and now we use the Held inequality. So it's like mod u raised power of p, the Laplacian is u of raised power of p, and then we have u mod du 2p minus 2 and this exponent will be in times mod u. Whole exponent is p upon p minus 1 whole square of p minus 1 divided by p, and this is less than equal to some constant time the L infinity norm of u, and this is the less than equal to the L2 norm of d to u. So LP norm of d to u. And finally, this last integral is nothing but integration of p over u of mod du is power of 2p, and whole is power of p minus 1 divided by p. And thus, on the left hand side, we have this thing. This implies mod du will 2p whole is power of 2p minus, and the 2p power is here, the power is 2 upon p minus 1 less than equal to c times the L infinity norm of u and the LP norm of d to u, which is nothing but actually the square of d2 L2p, which just implies that du L2p is less than equal to some constant time the L infinity norm of u whole power half d2u lpu whole square of half. And this is the required inequality which we wanted. And this holds for all u in CC infinity u. So next, what we are interested in is the analogous of one thing which we saw in distribution theory as well, that if the derivative is zero, then the function has to be constant. So it's like more or less the same thing we will see that if the weak derivative is actually zero almost everywhere, then we see that the function is used constant again almost everywhere. And to prove that, we will use this idea of modifiers. So we'll see that how easily we can show that. So suppose U is connected and U belongs to W1P Q satisfies du equal to 0 almost everywhere in U. Prove U is constant almost everywhere in U. So this is the same thing which we saw in the classical theory as well as distribution theory, and the same thing holds here as well. So to prove this, the proof is actually quite easier when we are considering the case of this Sobolev things. So the solution is first consider u epsilon to be all those x in u such that the distance of x with the boundary of u is greater than epsilon. So if my u is something like this, the u epsilon is something in the inside region. So this thing is u epsilon. So for x in u epsilon, consider the function u epsilon x to be integration of uh, consider the integration of pi epsilon x minus y du y dy, and this is the integration over. I'm taking y to be u epsilon. So the x minus y is actually inside in u only. So this is actually where pi epsilon is the standard modifier. But sorry, so this is u only uy. So this is a convolution which I'm considering. And then we know that that u epsilon is in the infinity u epsilon, and since this is in C infinity u epsilon, the derivative du epsilon of x, nothing but the integration of this phi epsilon x minus y of duy dy. So the derivative is transferred to the function d. So we can do this because we have this u to be in W1P. So this du is in that sense, that weak sense. And what do we have? We know that d u is 0 almost everywhere. What this basically implies that du epsilon is x is 0 for all x in u epsilon. And what this basically implies that u epsilon is constant in u epsilon, and this is constant. Also, we have u epsilon minus u of LP, u epsilon. This goes to 0 as epsilon goes to 0. What this is basically implies, we have, so this is a u epsilon is a sequence of constant functions. So when this converges, it has to converge to a constant function only. What this implies? This implies that because we have a pointwise convergence, and every sequence is actually a same sequence, so it has to converge to the same limit. So what this implies? This is implies that u is constant almost everywhere. So that's the easy proof to prove this the same analogous result in the Sobolev spaces. So next, we have another thing that the embedding which we talk about this Sobolev embedding when my p is equal to dimension only p is equal to n, and in that case, what we saw that this this Sobolev space W1n is continuously embedded in any LP space where p is greater than equal to 1, but it's not in the L infinity space. Like we are not able to show that it is in uh, the L infinity space. So we have one more example which says that we have a function which is in the W1n space but is not bounded. So we have another function. We saw in one in the video lecture, but we have another one. So verify that if n is greater than 1, the unbounded function u equals to log of 1 plus 1 upon mod x. This belongs to W1n u, or u is equal to unit ball So we have to prove that this function is actually W1 in U space. So we have to first to prove this is integrable, and then we have to show that this derivative is also integrable. So integration of U of mod ux dx is nothing but the integration of mod u of log of log of 1 upon 1 mod x dx. And since this n, so I have to take the whole power n. Next, this actually can be done inside the polar coordinates to be omega n minus 1 integration r from 0 to 1 mod of log of 1 upon 1 plus r whole power n, r is power of n minus 1 dr. So this is a continuous function except it has singularity at r equal to 0. So this integral, let's name it to be I. So I is finite if and only if the limit as r tends to 0 of this log 1 upon 1 plus r whole is power of n times r is power of n minus 1. This actually exists. The existence is enough. So when my r is between 0 to 1, so when r is close to 0, so 1 upon r is sufficiently greater than 1. So log of 1 plus r is again positive. So I can take this whole thing is equal to assume that to assuming it to be the limit r tending to 0 log of log of. So this limit exists if and only if this particular limit, if we consider log of 1 upon 1 plus r, well, we don't need really any power here. And this is actually r of n minus 1 whole divided by n. And this actually can be validated as the L'Hopital rules. So this is limit r tending to 0 log of log of 1 upon 1 plus r whole square of r of 1 minus n whole divided by n. This is limit tending to 0. So again, don't really have to worry about the case for this. So let us try to apply the L'Hopital rule. This is 1 upon log of 1 upon 1 plus 1 by r. And this we have 1 upon 1 plus r, 1 plus 1 upon r. And this is nothing but minus 1 by r square whole divided by 1 minus n whole divided by n. 1 minus n whole divided by n minus 1. So all of this can be written as limit r tending to 0 n upon n minus 1, and this is 1 upon log 1 upon 1 plus r, 1 upon 1 plus r, and there's one more r, and the r is power of 1 minus 1 minus n whole divided by n. This is nothing but limit as r tending towards 0 n upon n minus 1, 1 upon log of 1 upon 1 log of 1 plus 1 upon r, 1 upon 1 plus r is power of n minus 1 whole divided by n. This limit actually is 0 only because log of 1 upon 1 plus 1 upon r is nothing but r into 0. This actually tends to 0 only. And so this thing is actually, and r is also having a positive power. So we have this thing to be this thing to 0. So this implies that I is finite. So the u is in ln. So next we have to evaluate next we have to check whether we have this the derivative of u, the weak derivative u to be in ln or not. So let sin cc infinity of u, then what we have to consider, we have to consider the weak derivative. So before evaluating the weak derivative, we know that whenever 4x non-zero, ux is this thing, right? Log of 1 upon 1 plus r. Right. So what we can do, we have a we can actually so sorry, this mod x. Del u by del x I is nothing but del u by del r and del r by del x1. So which is nothing but 1 upon log of again 1 upon 1 upon mod x plus 1. And this is 1 upon 1 plus 1 upon mod x. And this is we have to differentiate 1 upon mod x. So that is actually minus half uh, x1 square upon x1 square. 4 is power of minus 3 by 2. So then we have twice of xi and all multiplied by xi divided by r. So this is the del r by del xi. This whole can be written as 1 upon log of 1 plus mod x, 1 plus mod x minus xi square divided by r is power of 4. So this actually will imply that mod of gradient of u or du is less than equal to 1 upon log of 1 plus 1 upon r into 1 plus 1 upon r, and we have this whole thing to be 1 upon r square, which is 1 upon r times 1 upon 1 plus r into log of 1 upon r plus 1. So finally, if you take the risk, so this what this gives, if we have u grad u whole square of n is actually less than equal to the whole u 1 upon mod x 1 plus mod x log of 1 plus 1 upon mod x dx, which is by polar conversion omega n minus 1 0 to 1 of whole square of n as well, rn minus 1 rn 1 plus r whole square of n, and then we have log of 1 upon r plus 1 whole square of n dr omega n minus 1 0 to 1 1 upon r times 1 plus r whole square of n, and then we have log of 1 plus 1 upon r whole square of n dr. So now we have to see whether the right hand integral is finite or not, and this thing actually goes to even the one infinity, but actually this integral is finite, and that can be checked. So if I consider I2 0 to 1, it's enough to check. So one can check this dr r log of 1 upon 1 plus r whole square of n, and this thing actually is if we substitute actually this integral is finite whenever our r times log whole square of n is n power is greater than 1, so that is finite. So we can actually take the substitution as well. We take this to be t, then we have 1 upon 1 upon r dr. So not really this minus 1 upon r square dr dt, and this is nothing but when r is 0, we have infinity, and log 1 is log 2 dt, and this actually implies minus dr r plus 1 times r equal to dt, This also implies that 1 upon 1 plus r is e to the power of t. It just implies this is r is nothing but et minus 1 whole inverse. This is dt whole divided by t to the power of n. This is actually a minus dt of r plus 1, and r plus 1 is 1 plus et. Let me write this in a better way. 1 plus et minus 1 whole inverse dt. And this actually whole can be written log 2 infinity of 1 plus et minus 1 whole inverse. And et, since we are considering from the 2 only, so it's like dt, and then you have t to the power of n, and we have this et minus 1 is actually non-negative here whenever I'm taking, since t is greater than log 2, but this implies that et has to be greater than 2, and this which implies et minus 1 is actually greater than 1, so it is again strictly positive. So this numerator is actually always can be shown to be less than equal to twice of log 2 raised to infinity dt by t raised to power n, and which is finite since n is greater than 1. So this is finite, and since this is finite, we have this derivative to also be in the ln space, and when that is the case, this implies thus we have this u to be in w1 comma n u. But what do we have here? We have this u is certainly not bounded. It's not in L infinity because of the uh, singularity at x equal to 0. Okay. So finally, we have one more question, and the results which we saw in classical theory may not always be lifted up to the Sobolev spaces. And so next question is actually reflection of this fact only. So we know that if we have a function which is bounded, and if its derivative is uniformly bounded, then what we basically have here is that the what we have basically there is that uh, the function is turns out to be Lipschitz constant. The Lipschitz continuous. So if my derivative is bounded, uniformly bounded, then the function then the function itself turns out to be Lipschitz continuous. So that is not the case when we have the same thing lifted to the Sobolev spaces. So in the Sobolev spaces, if it's weakly bounded, it may not be the case that the function it turns out to be Lipschitz continuous. So uh, so the next question says that give an example of an open set U subset of Rn and a function U in W under infinity U such that Q is not Lipschitz continuous on U. So this is quite non-trivial or quite surprising to have this type of results, which is quite not intuitive. We expect this to be the case, but that is not the case. So, uh, what is the function we would have? If we consider A to be the set, when we have this terms of polar coordinates r comma theta, and then I'm considering r to be just from 0 to 1. So unit ball, punctured unit, in fact, punctured unit ball, and we have this theta to be between minus pi to pi. So we are just not considering these the slit, which is on the negative real axis. So that if I'm considering the subset of R2, then define fx y as x square plus y square. So this is r square only times c. So this is r a tan 2. This is so this is the modification of tan inverse of xy, where a tan 2 xy is defined as, so this is actually tan inverse of y by x, and x is positive, tan inverse of y by x plus pi if x is negative and y is positive, or no negative we can also take, and then this tan inverse of y by x minus pi if x is negative and y is also negative, and this pi by 2 when is actually x is 0 and y is 0. X is 0 and y is positive actually, not 0. And finally minus pi by 2 when x is again 0 and y is less than 0, and this is undefined when x is 0 and pi 0. So clearly this I know that tan inverse function is actually a bounded function. It lies between minus pi by 2 to pi by 2. So this a tan 2 is again a bounded function. And this x squared plus y squared in the unit circle is again bounded. So this is a bounded function. What more? If we have considered the partial derivatives, so del f by del x of xy. So we only need to consider the partial derivatives when we are in the quadrants, the four quadrants, accepting the uh, not considering the boundary of this quadrant. So basically the x and y axis. So then this would be, so first of all, we have this the case whenever x is positive and y is anything. So for the first and the fourth quadrant, this is just tan inverse y by x. So this is 2x tan inverse y by x plus x square plus y square. And this is with respect to x. So this is 1 upon x square plus y square whole divided by x square. And we have y upon minus y upon x square. The next is we have the second quadrant. So x is less than 0 and y is positive. So then our a tan 2 is tan inverse y by x plus pi. So this is 2x pi plus tan inverse y by x. Then again you have plus x square plus y square. And the same thing because pi doesn't constitute when we consider the derivative. This is nothing but minus y upon x square plus y square. And finally we have if x is less than 0 and y is less than 0. So in the third quadrant, so we have this is tan inverse y by x minus pi. So this is 2x minus pi plus tan inverse y by x. Plus again we have x square plus y square times minus y upon x square plus y square. So we can see in the all the four quadrants, this is again a bounded function that is partial derivative with respect to x. Likewise, we have del f by del y from x comma y, which is 2y tan inverse y by x plus x square plus y square times x upon x square plus y squared if x is positive. Next, we have this second quadrant if x is less than 0 and y is positive. So this will be twice of y, pi plus tan inverse y by x. And then we have this x square plus y square times 6 upon square plus y square. And finally, we have the third quadrant. X is less than 0 and y is also less than 0. Then this will be 2y minus pi plus tan inverse y by x plus x square plus y square x upon x square plus y square. So clearly, Others, the if x and y axis are major zero. So clearly we have uh, the del f by del x and del f by del y belongs to the L infinity of A. Thus, what we eventually have, thus we have finally we have this the function which I have defined f to be in w1 comma infinity of A. But if you consider this thing, so but if we have mod of x comma y, this is half only, and theta is one is theta one theta I would say theta one epsilon to be pi minus epsilon, sorry, pi minus epsilon, and theta 2 comma epsilon to be minus pi plus epsilon. So we have basically 2 points in the unit circle. So the in the radius half, I'm considering 2 points, one in the just close to angle pi, and this just close to angle minus pi. So we have so actually better write this to be from R. So we have f of R of theta 1 epsilon to be, this is nothing but x square plus y square. So this is 1 by 4. And what is tan inverse? So a tan xy is just gives you the angle only. This is pi minus epsilon. And f of another r is 1 minus theta 2 comma epsilon. This is nothing but 1 upon 4 minus pi plus epsilon. And we note that this the difference of this r comma theta 1 comma epsilon minus r comma theta 2 comma epsilon. This actually this difference tends to 0 as epsilon tends to 0. But what is this f of r comma theta 1 comma epsilon minus f of r comma theta 2 comma epsilon? This is nothing but this is 1 by 4 of 2 pi minus 2 epsilon, which is nothing but pi minus epsilon by 2. And this actually is not tending toward 0. So this is not even continuous. So this is not even ellipsis. So but even it's not even continuous. So because of this, we have this contradiction that so this is not contradiction. So this is what this implies. This is we have this implies that is not ellipsis continuous. Because of this, we have issue, and with this we have something not intuitive thing in Sobolev space. So with this, we end our session today. Thank you.